Hey everybody, welcome to the next installment of Statistics in Pajamas. We're going to be sticking with our analysis of variance theme, but this time we're moving into factorial analysis of variance. With the one-way analysis of variance that we covered last week, we only had one treatment variable, or one variable that identified the groupings for our data. But all that a factorial analysis of variance is doing is it's allowing you to add additional treatments or additional grouping factors to your analysis. As one example, imagine that you're a silviculturalist and you would like to see how different types of silvicultural treatments impact biomass storage on your forest. So you have two different types of silvicultural treatments that you want to compare. Even age treatments like clear cuts and uneven age clear cuts, say for example single tree selection or thinning. But it's often more complicated than just what type of silvicultural treatment you apply that impacts biomass. There might be stark differences right after treatments are applied, but over time those differences begin to fade. And so by adding in a second treatment variable, a second grouping variable for rotation length, where we're looking very soon after the treatment, about 50 years out from treatment, and then again about 100 years out from treatment, we can not only test whether or not there's differences in even age and uneven age harvest types, but we can also see if there's differences over time. And this is the really fun part about the factorial design. We can also look and see if there's an interaction between rotation length and harvest type. And that's what makes the factorial ANOVA really powerful, because you could do a simple one-way ANOVA just for harvest type and make some conclusions, or do just a simple one-way ANOVA for rotation length and just interpret that. But what the factorial analysis allows us to do is it allows us to account for the variability that both of those influence, and then also look at how they interact. Just to get you used to some of the terminology, when you're running a factorial ANOVA, it's most common to try to have the same number of observations falling into each of the different grouping levels or each of the different categories for each of your treatments. That's a nice balanced design. And when we're talking about these balanced or factorial designs, we can often describe them by how many grouping levels there are for each of the treatments. So in this example, we have 3 different levels of rotation length, 10, 50, and 100, and 2 different levels of our harvest type, even aged and uneven aged. So that's essentially a 3 by 2 factorial analysis of variance. The hypotheses that we're testing with the factorial ANOVA are the same as we did with the one-way ANOVA, right? The null hypothesis is just that our groupings are the same. There's no difference in the mean between our different groups. And this time the only difference is that we have more than one hypothesis. So a factorial analysis of variance is actually testing multiple hypotheses simultaneously. And again, that's the key, is that we're actually going to partition the variance between those treatments and our error in that factorial in the ANOVA table. And just to break down how this really is exactly the same thing we were doing before with the one-way ANOVA, notice that we still have our ANOVA table, and we still have our degrees of freedom and the sum of squares and the mean square, and then the F statistic and the p-value associated with that. The table looks exactly the same. We're just adding additional rows here, a new row for each variable that we're including, right? Each additional variable that we're including. And then we still have our error term. This would be our within term. So don't get confused. You won't see it referred to typically in factorial ANOVA as that within sum of squares or sum of squares within. Instead, you'll see it referred to typically as error. But the formulas remain the same for the sum of squares between for those different treatments. We're doing all these other calculations the exact same way. Okay, really, the only difference is how we are calculating our sum of squares total, right? We have to make sure that we're adding up all of our sum of squares for our treatments, for both of them or however many we have, and then also tacking on that error. And that's going to give us a sum of squares total, which is essentially how much variability there is between every single observation and the grand mean. So we can calculate the sum of squares total, and that will often help us get to the error. If you're not doing this by hand and filling out that ANOVA table by hand, and you are doing it in software like Jump, one thing just to be aware of is that sometimes these software packages will break down that ANOVA table into two different sections. They'll have it in a total model section where they actually are summarizing all of the different treatment variables you have into one line. So this model would be all of the different possible treatments that you were considering. In this example, we had 4 different treatment variables we were considering simultaneously. That model line up there is just summing them all. Literally sums the degrees of freedom, sums all of their sum of squares, and then calculates the mean square and the F ratio from that. And this is really just set up if you were trying to examine how, in sum total overall, how well do these different variables categorize or quantify the variability in our data. In this error term here, this is still our sum of squares within, so that hasn't changed. The only problem is it's a little bit harder to calculate this when you have so many different groups to try to calculate the within for. And so as I mentioned earlier, typically what you'll do is you'll quantify your total sum of squares and then just take the difference between this total and your model, and what's left over is your error. You might say, great, there are multiple different variables that I'm interested in testing. So why not just run them all individually? Why not just run a one-way ANOVA for each one? Well, I already mentioned earlier that what's nice about doing the simultaneous testing is that we can also look for interactions between those groups. So maybe there's a difference between one of my treatment groupings, but only at the setting of one of the other treatment variables. That interaction piece is one really nice added bonus of this factorial analysis of variance. But the other thing is that think about what an ANOVA is doing. It's partitioning that variance into what can be accounted for by the between groupings or by that treatment, identifying what group you're in based on that treatment, versus how much variability there is just due to error. And so what's nice is that each time you add another treatment variable in there, you're essentially reducing that error term. There's only so much variability in a data set. But the more of that you can account for with your different treatments, the more likely you are to isolate the impact of each of those individual treatments, because you're essentially reducing that error term. And remember that your F statistic and ultimately the p-value that's associated with that are determined as the ratio of your sum of squares between to your sum of squares within. That's your error term, the within. And if you reduce that error term, it means you're more likely to isolate the variability and have a higher F statistic for the treatments that you're looking at. And because of that, you'll often see factorial ANOVAs used specifically to isolate one treatment of interest. And for example, there are a lot of studies where there will be a control variable. They don't really care if there's a difference in this variable. They're not running this ANOVA to test for differences. They just know that inherently this variable does introduce variability to the data, and they want to control for that so they can better isolate the impact of the treatment they truly are interested in. Imagine you were looking to see if there was a difference in the amount of weight gain for 3 different feed types. We'll just call it food A, B, and C. But you know that different mice put on different weight based on their genetics. Some mice can gain weight really easily, and some could never gain weight no matter how much they eat. People are like this too. So we know there is some genetic variability, and we would like to control for that. So we can actually introduce this second treatment variable, which we'll call litter, which has 10 different levels. So there's 10 different litters that we were trying to block for. And that's going to help us identify whether or not we really do have a significant difference in our food sources. And these are known as randomized block designs because we typically will randomly apply certain offspring from each of these litters to each of these different food types. So just to give you an idea of what this looks like, it's not a black box. We can do this in Jump and it's going to be so easy. You click a couple buttons and bam, there are all your results. But I just want you to recognize that the math behind this is not any harder than what we've already been doing. there's just more of it. For each of our individual treatments, so for example, our 3 different food types, we're doing the exact same thing we did before. And this spreadsheet is set up to make it really easy. We just added a column. Here's the grand mean. It's just repeated over and over. Here's the mean for each of those diets. This was diet 1, diet 2, and diet 3. Right? And here are the means for each of our litter blocks. So 11.53 was litter 1. If I come back down here to litter 1, there's 11.53 again. And so I'm doing this over and over. So essentially I'm getting the mean, here's my grand mean, and the mean for each of my groupings. And then all that I have to do is do some math. So for the total variability, I just take that little mouse's weight gain, right, and I subtract that from the overall mean. That's what I get right there. And then I do the same thing for my treatment. This is the diet. I'm just taking that treatment mean and I'm subtracting the overall mean for that, and that's what I get right there. Do the same thing for litter. So I take that litter mean and I subtract it from the overall mean, and that's what that is. And then all that this error term is it's our total error minus each of these. This is what we're left up with. So literally these are our deviations. We square them, then we sum them up. So here's our sum of squares total, treatment, which was the diet, the block, which was the litter, and the leftover. So we've literally just done the exact same math that we did with our one-way ANOVA, only over and over again, and that's going to allow us to start filling out our ANOVA table. We had 3 diets minus 1, that gives us 2 degrees of freedom. We had 10 litters minus 1, that gives us 9 degrees of freedom for the litter blocking variable. The sum of squares, we just added up over here. We divide sum of squares by degrees of freedom to get the mean square, and then we take the mean square for each of our treatment variables, here a treatment and a blocking variable, divide that by our mean square error, and that's going to give us our F statistic, which we can then plug right into Excel with that f.dist function. So we end up with our p-values, and notice we'll have a p-value for each of our treatments. So we can see that this is actually an exponential to the -9, so this is a highly significant result, 0.000000000225. Litter, that blocking variable for litter, is also significant. Remember, I didn't care about differences in the litter. I didn't really want to know if litter 5 was the fattest. I just wanted to block for that variability. So I can actually ignore this when I'm discussing my results, and I can just say we blocked for differences in genetics using the litter grouping and found that the 3 treatments were significantly different. When we're running a factorial ANOVA in Jump, we can't use that FitY/X platform because FitY/X is meant for just 2 variables, one response and one independent variable, and we're purposely trying to test multiple variables. So we have to come into this fit model platform, which is going to allow us to create whatever model we want by adding these variables. We can highlight them and click add, adding them into this model effects box. Our response variable is still going to go up here in our Y response variable. So let's just pop right over into Jump and take a look at this. So when I come up here into Analyze, I can't use this FitY/X anymore because I have more than 2 variables I'm testing. So I have to come into this Fit model. And I can still enter my response in there, but now I'm saying I'm interested in whether or not there's a difference between these diets, but I know I want to block for which litter. And so I can enter them both, and then I can click run and run this. And I wanted to spend a little bit of time going over this output because it does look a little bit different than what we've seen before. There's a lot here, and we'll break it down. First of all, just know that the Fit model platform assumes that you're trying to make a predictive model, because usually that's when people start throwing a lot of variables into an analysis. And so it's really giving us a visual of if we wanted to predict how much weight gain there would be based on diet and litter, how close will we be to the actual weight gain. So it's actually a pretty nice fit here, just using these 2 variables, diet and litter. We're accounting for about 91, almost 92% of the total variability in this data set. So this was something we could come back to when we're discussing how meaningful these results might be. In sum total, how does these three different diet groupings and litter, how much of the variability, how significant is this model? Highly significant. If we wanted to look at the individual variables, we can see that the diet treatment is significant at the 0.0001 level, but so is that litter block. So again, we'd have to discuss how there was a significant difference between these litters, which means genetics still plays a significant role in our understanding of how much weight is gained regardless of food. But we wanted to block for that so that we could isolate this effect. And so we see even when we're accounting for this variability, we still see a difference between groups. Okay, if we wanted to account for how much variability the litter can account for, we can still do the same thing that we did before with the one-way ANOVA. We can take that sum of squares total, and we for the litter or for whichever treatment we're interested in, and divide that by the sum of squares total right here, and that's going to give us the proportion of variability that each of these can by themselves account for. So for example, we can see here that both the diet and the litter were significant. The sum of squares for that diet treatment was so much higher, 69, almost 70 sum of squares out of 104. So that's all over 70% of the total variability in weight gain is accounted for just by this diet treatment block. Okay, and then the litter block tosses in roughly another 25%. So that still doesn't help us figure out where the differences are, right? That ANOVA is just an omnibus test. We have to come back over into these little effects test regions of our output to figure out where those differences lie. And as you may have guessed, if we go to the magic red triangle, we can ask for a comparison of each of these means, right? We can ask for the student's T, we can ask for the Tukey's, honestly significant different, or the Dunnett. We know we use Dunnett when we have a control. We don't have a control here. We know we use student's T if we want to do a Bonferroni adjustment. I don't want to. I'm going to stick with the Tukey HSD. And it gives us this nice matrix of the least square means differences. But again, it also gives us the nice connecting letter reports, which are often a lot easier to interpret. So here we can see that they don't share, none of these share the same letter. So none of them, they're all significantly different from each other. Right? So this is one of those extra pieces of information that we need to be able to interpret our results. We have a significant result. Luckily we used the blocking factor because it was significant, but still the majority of the variability is accounted for by this diet treatment, and here is how those diet treatments actually differ from each other. We didn't really care about litter, it was just a blocking factor. But there are other data sets and other times when we actually will care about those differences. Okay, here's an example where we're still looking at deer mice, and we're still looking at different diets. We have two different diets here that we're looking at, but we're also interested in differences in gender. Maybe males respond one way to different food inputs and females respond another. So here we have their raw value weight. Oh boy, the fact that you see ranks here probably already gives away that I figured out that my weights were not normally distributed. So let's just verify that for you. Hold on, I'll pause till I get to the end. Yeah, as suspected, here are the results of my goodness of fit test, and you can see that I am below 0.05, so I have to reject the null. The data is normal. I do not have normal data. So that's one of the problems with the fit model platform. We don't have a magic red triangle to automatically rank or apply some non-parametric test for us. So when we're in this factorial analysis fit model window, we do have to make our own transformations, and I chose to go with the ranks here. So that means I'm going to be running this analysis on the ranks, not on the raw weights. So when I come up in here to my fit model, I know that I need to use the ranks as my response, and I'm actually interested in both diet and gender. But maybe it's not just that I want to know if the males can get fatter than the females, or if diet 1 or diet 2 is better for putting on weight. Maybe I'm also interested in the interaction. So in other words, does which diet works best really depend on whether you're a male or a female? To figure that out, I have to test the interaction. And in Jump, it's really pretty straightforward. I just highlight, I held down the control button there, I highlight the two variables I'm interested in, and I just ask to cross them. And there they are. I now have the interaction term added to my model here. So now when I run this, I'm going to see the output again for that full model, right? There's the R-squared for everything. Here's the analysis of variance for the entire model summed up. I am interested in the effects. In other words, how significant are each of these different treatments, the diet treatment, the gender treatment, and their interaction. And what I can see here is that I don't have a significant difference between those two diets. I don't have a significant difference between the males and females. But how interesting. Look at this. I do have a significant interaction between the two. And this is very common. Okay, it's very common that if there is a significant interaction, meaning that, sure, there's a difference between diets, but only for one of the genders, or conversely, yes, there's a difference between genders, but only for one of the diets. That means that the relationship isn't the same, or the difference isn't the same for both settings of the other treatment variable. That's what an interaction is. And often because of that, it'll wash out the significance of the individual treatments because it's significant half the time and not significant the other half of the time, right? Depending on which diet you're doing or which gender you're in. So this is why the interactions become really helpful. So when we add an interaction, we're essentially adding another variable to the analysis, and that would have its own null hypothesis that we're testing. So we're saying that the values, the measurements for each possible combination of groupings, so here it would be for even age stands at 10 years, is going to be the same as even age stands at 50 years, which is the same as even age stands at 100, and so on and so forth. The hypothesis, the null, is essentially saying that for each possible combination of these treatment groupings, you're going to see the same mean. What this would look like is if you saw the same difference regardless of the settings of some second variable, you would expect to be able to plot out these lines and see that they don't cross. So here's an example. Here we have a high treatment and a low treatment. Here we have the males would be the diamonds, the squares would be the females, and so you're seeing that regardless of your gender, whether you're a male or female, diet low, or whatever this treatment is, the low treatment is always higher than the high treatment. Okay, and similarly, the males are always higher than the females, regardless of which treatment you're in. So there's no interaction here. The relationship stays the same. An interaction, however, would mean that the relationship differs depending on which group you're in. So in this example, if you are a female and you're a square, it's the high treatment that results in the higher loss. But if you're a male, here in the diamonds, it's the low treatment that results in a higher loss. The opposite effect. The treatment has an opposite effect depending which gender you are, male or female. So that is an interaction. And if we hop back into Jump here, as you might expect, Jump has a nice gem hidden in the magic red triangle that might help us to visualize those interactions. So if we go to the main magic red triangle and we come down to factor profiling, it will allow us to actually see interaction plots. So it's going to visually graph out for us what those interactions might look like, and then it tacks it on to the end. Sometimes these are really hard to see, so I like to drag them and make them a little bit bigger so that I can really see what these lines are doing. So we can see right off the bat that for our diet groupings, we had two different diets, and for our gender groupings, we had two different genders. When you plot those out, we see a cross, so we know we have a significant interaction. Well, which we knew anyway because our interaction shows up as being significant down here. But how to interpret it? Well, the first thing I want to tell you is that these two figures are mirror images of each other. Here you have the diet on the x-axis and the male and female plotted out as different lines. Here you have the male and female on the x-axis with the diets plotted out on different lines. So they're telling you the same thing, just in different ways. So my advice to you is to just pick one and go with it, and then don't be confused by the other. It's telling you the same way, but in the inverse, and sometimes that inverse is confusing. So I don't know, let's just stick with this one. I've got the females plotted out here and here, and I've got the males plotted out here and here. Diet 2 is in blue, diet 1 is in red. And what I'm seeing is that for females, diet 1 has the highest response, but for males, it's diet 2 that has the highest response. Now, sometimes these interaction plots can be a little confusing. I find them helpful, but I think it takes a little bit of practice. So if you wanted, you could always come back over to your magic grid triangle for the interaction variable, that term, and run your Tukey's honestly significant difference to compare those means. And when I do that, what I really see is that those two males, they share the letter A. So for the males, it doesn't matter whether they're on diet 1 or diet 2. There's no significant difference. But for the females on diet 1, they are significantly higher than the females on diet 2 because they don't share the same connecting letter. There's no B up here, there's no A down here. So this is telling me that diet makes a difference for females, but not for males. I usually use a combination of them both. Right? I come down and I look to see whether or not I really do have the cross. Is it just that one isn't significant but the other one is, or are they significant in opposite directions? And then I'll come over to my connecting letters to start seeing, well, which is the highest, which is significantly different from which other. So that was your crash course in Factorial ANOVA, and let me tell you, that was a crash course. I would highly suggest reading through our crib notes and making sure that you're in class when we go over some examples. But the next step is still, how do you not just interpret all of this, but summarize all of it? When we are into these much more complicated factorial ANOVAs with multiple variables, we have to summarize each of those, right? We can't just talk about one variable. We're going to have shorthand for anything that's significant. And so you would have to do the same things you've done before, where you're stating what the hypothesis was, what test did you run, include the shorthand for any results that were significant. If there weren't other significant differences, just mention those as well. Describe the interactions, and then give your interpretation. Not that we're doing anything different, but again, we're just doing more of it, so it becomes a little bit more complicated. And we still have to think about how meaningful something is. So I actually would have tossed in here, right, that I had an r squared equal to 0.28, and I might even come back and compare that sum of squares to the total sum of squares up here so that I could figure out how much of the total variability each of these different treatments and the interaction account for. And that's going to help me not only interpret overall how this model works or how meaningful this model might be, but how meaningful each of my individual variables are. Because again, remember, we're not necessarily trying to build a model here with the factorial analysis of variance. We're trying to test whether or not these different variables are significant, whether or not they are meaningful, and so that's where that individual r squared would come from for each of these different treatments. And then also whether or not the significance and how meaningful these differences are depends on some interaction. Hopefully this has been eye-opening. I would assume that most intro stats courses don't get into factorial analysis of variance, so consider yourselves either lucky or cursed.